Welcome back, everyone. In this lecture, we're going to have an overview of your project exercise for principal component analysis. And in the next lecture, we'll go through an example solution. Let's head over to your exercise notebook. Okay, here we are at the exercise notebook. Let's go ahead and take a look at the goals of the project and what you'll be doing. The overall goal is to figure out which handwritten digits are most differentiated with principal component analysis. So I should mention this is pretty much a solved problem already, and the data set is actually very common. It's called the handwritten digits data set. If you've done anything with image analysis with Python, you've probably run into this data set before. What we're going to be doing is using principal component analysis to take kind of a different approach or look at this data set and see if we can reduce the number of dimensions to just get an intuitive understanding over what digits are really easy for a machine to understand and read versus which ones are harder. So essentially, we're going to be pretending that we're working on an image recognition service for a postal service. And typically what happens nowadays is if someone handwrites the digit or address on an envelope, that address is actually read by a computer. No actual human is reading that, and it gets automatically sorted and sent out to wherever that package or envelope needs to go. And so what we want to be able to do is figure out where are the trouble spots for certain numbers that may appear similar to each other. That way we can hopefully gather even more data to train a machine learning algorithm on. So the process that we're going through here is not to actually recognize what digit is being shown, but to figure out what digits are kind of the troublesome digits. So the data background is essentially just a bunch of samples that were used for training, and someone had a bunch of people write down handwritten digits on a tablet, and then based off the pressure of that tablet, they created a digital image of that handwritten digit. So to complete the tasks below, what you're going to do is first read in the data set, and you realize that the data set is a data frame with the pixel values. So pixel at index or position 00, position 01, 02, 03, and so on. So it's 65 columns. So we have an 8 by 8 image of pixels, and the very last column over here is the number label. So this was the handwritten digit 0. This was 1, 2, 3, 4. This was the handwritten digit 9, 0, etc. So you notice the first one is a 0, and these are all the pixel values at the location. So if you scroll down, what we're going to have you do is create a new data frame called pixels that essentially just drops that number label column. So we have just the features. Then you'll go from a Pandas data frame to grabbing a single image row. So here we have that series, that single row here. And you can convert that to a NumPy array. And there's lots of different ways you can do that. You can check out a Stack Overflow post if you want. And then you'll convert that or reshape it to be an 8 by 8 array. So you'll go from just a straight 64 digit line or row to an 8 by 8 two-dimensional array. And then you'll notice you can use Matplotlib or Seaborn to display this. And here we can kind of see the 0 itself. So this is done with Matplotlib. Keep in mind that these values are essentially just going from 0 to some value depending on the pressure on that tablet, which corresponds to kind of the darkness or brightness. So you can see here, it's up to you to choose what CMap or color mapping to use. This actual value here doesn't mean that it's yellow, so to speak. It's essentially a black and white image. You can use CMap gray or CMap viridis or magma to choose any coloring you want. You can even use Seaborn to directly put on top the annotation of the values themselves. So lots of different ways you can do this, but essentially just want you to plot out on kind of this 2D grid to see a heat map of the corresponding values and the digit. So here we can see the very first row does in fact look like a 0, and it's only 8 by 8 pixels, so 64 pixels total. Now 64 pixels technically means 64 features. So what we're going to move on to is principal component analysis. So you're first going to scale the data, and then you'll have the scaled version of that number. Then you're going to perform principal component analysis to go from the pixel data set down to 2 components. So what does that actually mean? It means you're going from a 64 feature data set down to 2 principal components. So you're essentially doing a dimension reduction from 64 to 2. You're going to treat each particular pixel as its own unique feature. Then we're going to check how much variance is explained by the 2 principal components. You should get around 21.5% variance explained by 2 principal components. Then you're going to create a scatter plot of the digits in the 2-dimensional PCA space. And this is kind of the crux of the entire project. Can you create a plot that looks like this? So you have principal component 1 and principal component 2, and then we can see here the actual labels of those numbers. Recall that we had that number label column in the data frame. So you're actually going to have quite a few lines of code to create this nice looking scatter plot. And what you're going to realize, hopefully, is on the next task, which asks you which numbers are the most distinct, the whole idea here is we're looking for groupings that are well separated from the other numbers. So for example, we can see here this orange kind of cluster or clumping, if you will, is the number 4. And it's not on top of any other numbers, which is basically telling you that even when you reduce from 64 pixels down to 2 principal components, it's quite easy to see the number 4 being highly separated from all the other numbers, which implies that number 4 is easily differentiated from the other numbers, which means you probably don't need to collect any further data on this number 4. Instead, the troublesome numbers are, for example, the number 8. Notice that the gray dots are all over the place on top of other numbers in 2 principal components, which is a good sign telling you, hey, this number looks a lot like other numbers when you reduce it down to its principal components. So you probably want to gather more data on these numbers that have a lot of overlap. Okay. Then as a bonus challenge, and this is completely optional since we didn't really cover this sort of thing throughout the previous lectures, although we have mentioned it before, is to create an interactive 3D plot of the result when you reduce it down to 3 principal components. So there's lots of different ways you can do this. You can use it with Plotly or Bokeh, which are additional libraries, but see if you can figure out how to do it with just Matplotlib and Jupyter Notebook. Technically speaking, you should be able to create an interactive 3D plot without having to install an additional library. Now, I would definitely recommend using Matplotlib and Stack Overflow as a quick search to see how you can create this interactive 3D plot. And there's a special command line tool you can use to display it interactively in the Jupyter Notebook. So I'll kind of leave this as a bonus challenge. If you get stuck, don't worry, you can check out the solutions and we'll go through it there. But eventually you should get a plot like this that you can actually then rotate inside the notebook. Okay, so best of luck, and I'll see you at the next lecture where we talk about the solutions.